Okay, so good afternoon, everybody. Welcome to the Atto Fridays. Today, I was told that the time scales are going to be much slower by our speaker, but still, we are fine. We are flexible. As long as it's ultra fast, how you define fast is up to you. So it's a pleasure today to have Dr. Russell Means from Southampton as a speaker. He's an associate professor in the School of Chemistry at the University of Southampton. He obtained his PhD in 2005 under the supervision of Professor Helen Fielding. And then after postdoctoral positions at the University of Virginia and again at UCL, he was awarded a Royal Society University Research Fellowship in 2011. And then he moved to Southampton. In Southampton, he works on exploiting new optical technologies for studying complex chemical reaction dynamics in both the gas and solution phase. So we're gonna hear about liquids, we're gonna hear about gases, and we're gonna hear about scattering, you see? So I'm making some false advertisement here. But anyway, it's gonna be a nice talk. And today he'll talk about combining scattering and spectroscopic probes of dynamic electronic and geometric structure. Okay, so Russell, we're ready to go. The floor is yours.
Thank you very much, Carla, for the invitation. I would much prefer to be at UCL delivering this in person. It's always harder to deliver these talks online, I find, but hopefully, hopefully people can still follow what we're talking about. Okay, so yeah, I'm going to talk about some experiments we've been doing on small molecular systems in the gas phase. So we're going to focus on the gas phase, combining both structural dynamics measurements, so scattering measurements that give us a direct probe of geometric structure, and spectroscopic probes that give us a much more direct measure of electronic structure. And so we're talking about molecular dynamics. I'm a chemist, so typically we're talking on the order of a few to tens to hundreds of femtoseconds, that sort of time scale. So that's fast to me. I'm not quite Atto yet, but we're working our way there. So as I said, I'm a chemist, and so what we're interested in is trying to understand photochemical reactions, and photochemical reactions are complex. They involve the coupled motion of both electrons and the atoms within molecules. And if we take an example of what is a relatively small molecule by a typical organic chemist standards, this acetylacetone molecule, and we look at the photochemistry, we've got this kind of cartoon picture of what the dynamics are happening. So if this molecule absorbs a UV photon, we excite up to this second excited singlet state, S2, and then we start to move along the different potential energy surfaces of the molecule. So each one of these colored surfaces here represents a different electronic structure, different arrangement of the electrons, and that gives the molecule different driving forces. It's going to drive the molecule to rearrange and change its geometric structure. So upon excitation, the forces drive this molecule in one direction where we have a crossing between different electronic states, this so-called conical intersection, and that leads to a change in the electronic structure where the forces change again, and we start to drive the molecule in a different direction. This molecule can then undergo another series of different electronic transitions leading to states of different multiplicity. So this green state is a triplet state. This is our ground electronic state again. And then that can lead back to different fragments, different products in the end. And many of these channels might eventually lead to the same fragment. So in each of these cases, we're getting CH3 fragments produced, but they're occurring via very different processes. So they've got very different mechanisms associated with them. And that means they can have different internal energies, different rotational and vibrational energies within them. And that's going to be important for what the molecule can then go on and do if we are looking at things in the solution phase, for example. So if we're going to have any hope of understanding this sort of complex interplay between all of these motions, we're really going to need probes that are sensitive to every geometry and every electronic state within this system. If we start being too selective, we can maybe pick out, say, the initial dynamics on this first state or the formation of these products. But we're then going to have a really hard job unraveling what's gone on in this sort of cascade of motions that's occurred to get us from that starting point to that final point. And that's 6 or 7 years now, trying to come up with ways that we can get global probes of these motions. And so recently we've been working on using structural dynamics measurements. So we've been using ultra-fast electron diffraction techniques. And that gives us a measure of the geometric structure of the molecule. So the location structure of the molecule. So the location of the atoms within our molecule, if you like. And we've been using what is a relatively old technique, time-resolved photoelectron spectroscopy, but using new sources to ionize molecule and get information about the electronic structure of our molecules. So the arrangement of the electrons within our molecules. And these kind of schematics give you an idea of what's going on in each measurement. So in our electron diffraction measurements, we've got our UV pump laser that's going to come in, and initiate some dynamics within our molecule. That might be some dissociation, some isomerization, whatever process that molecule does upon absorbing light. And then we're going to come in with a variable delayed probe of an electron bunch, so an ultra short pulse of electrons. And those electrons are going to scatter off this charge distribution that we've got here associated with all these atoms within the molecules to produce some far field diffraction pattern. And then we can analyze that diffraction pattern and get information about the structure from that. In our photoelectron spectroscopy experiments, we've got similarly a UV probe that's going to initiate some dynamics. And in this case, our extreme ultraviolet probe, typically in our experiments, is then going to ionize our molecule, and we're going to measure the resulting photoelectron spectrum. And by changing the delays, we can capture the change in electronic state and move away from this black box picture of what's going on in a chemical system. So we can really uncover what's behind this sort of question mark in that dissociation reaction. There are a number of other techniques you could choose to use for these sorts of things. So X-ray diffraction is the obvious analogy to the electron diffraction. You could think of using things like Coulomb explosion, where instead of the high energy of the photons, you use the high field to generate that global probe where you can measure all geometries of your system. Okay. Get rid of this. And what we're going to look at, what we're going to use as our system to study these things, to try and get an idea of what we can and can't measure, what resolution we're going to need for moving on to larger systems, and what are the challenges associated with those, is what looks like a relatively simple system, carbon disulfide. And this has been kind of a benchmark system for a gas phase spectroscopist for a while. It offers a lot of advantages in terms of experimental ease, such as high absorption cross sections. But there's a lot of challenges in trying to understand even what this simple molecule is doing. The cartoon picture we have is if you have this linear ground state geometry in this potential well. Upon excitation, you go into a new electronic structure which wants to be bent. So you've initially got these driving forces that are going to bend your molecule, decrease that SCS angle, and you're going to get stretching motion of that CS bond as well. So you've got this combined bending and stretching motion. And as that molecule bends and stretches, you get dissociation along one of two channels. One leading to a sulfur singlet dissociation product in a spin allowed process, and one dissociation process that undergoes intersystem crossing leading to this spin forbidden triplet state product. So this cartoon picture seems relatively straightforward, but as with all sort of photochemistry, if you have quite a high pump energy, you end up in an absolute spaghetti of electronic states that are all coupled together and all complicate the dynamics. So upon excitation, 200 nanometers takes us up to around 6 eV, and we tend to be somewhere in this region where we put all of these states. We initially go into these singlet states, but as these sort of bend, you can see how they start to couple, they start to overlap, and you can get mixing between all these electronic states, which really complicates the dynamics and the direction that your molecule is going to want to go. So there's been a lot of measurements in the past on the dynamics of these systems. I'm just going to concentrate on 3 of them before we move into some of our work. And these kind of give an overview of what we previously understood about the dynamics of these systems. So the first one is a photoelectron spectroscopy experiment. This is one of the classic photoelectron spectroscopy experiments out of the Stolo group in Ottawa, where they looked at aligned CS2 molecules. So they use a non-adiabatic alignment, a strong infrared field to initially align their molecule before the UV excitation. And then they can look at not only the energy of the photoelectrons, so the spectrum that they get as a function of time, but they can also look at these sort of molecular frame or alignment frame photoelectron angular distributions. And the shape of these angular distributions tell you about the type of orbitals that you're ionizing from and the continuum as well. And so if you can analyze these, you can get a lot of information about the electronic structure changes within your molecule. So in these experiments, they see this very rapid decay. That's indicative of rapid motion out of this sort of initially populated geometry for the sort of linear molecule. And they see also aligned with that, these big changes in the photoelectron angular distribution. And that's indicative of really fast internal conversion dynamics. So your initially excited population in one electronic state is spreading amongst a large number of other states. And that's associated with the bending and stretching motion going on within the molecule. So we've got this rapid internal conversion motion aligned with this rapid depletion in that excited state population. Other measurements actually done before those looked at the branching ratios of the different products. So you remember I said we had these spin allowed singlet products and the spin forbidden triplet products. And if you look at the branching ratio between those 2 components, you find that the spin forbidden products are actually dominating the reaction yield. Now there's been a lot of measurements that have come up with wildly varying numbers for this branching ratio. But if you take a center of mass and an average of what are reliable measurements, it seems to center around about a branching ratio of 3. So these seem almost contradictory, right? We've got this rapid motion internal conversion dynamics in the singlet manifold, which seems to remove this population rapidly. But then we've got domination of the products by this spin forbidden triplet state. And we can start to get a bit more information if we increase the photon energies, for example, in those photoelectron spectroscopy measurements. This is some measurements out of the Suzuki group, where they have really exceptional time resolution for these type of measurements. So here they've got a time resolution on the order of around 17 femtoseconds or so between their UV and VUV pulses. And they can get a bit more information on that initial dynamic. So they see these large sweeping changes in the photoelectron spectrum as a function of that pump probe delay. And this really maps out that initial bending and stretching motion because we've got large changes in the ionization potential of the molecule. But even at these, what would be considered relatively high energies for most photoelectron spectroscopy experiments, we still can't capture all of the dynamics that are going on. We can't capture the effect of the triplet states that are competing with these motions. We can't capture the final products or the timescales on which those final products are formed. So we're still blind to a huge amount of the dynamics that are going on. Okay, so if we move on to some of the experiments we've been doing over the past few years, the first experiment I want to talk about is actually looking at the structural dynamics. So can we use some of this new generation of ultra-fast sources, X-rays and electrons, to try and get a more direct handle on the geometry changes that are occurring within molecules? So these experiments were done at the LCLS Mega Electron Volt Electron Diffraction Facility, and these were led by Rory Forbes, who's a staff scientist now at SLAC. And so in these experiments, what we have is we have our electron gun essentially coming from down this end. We recombine that with our laser at a small angle, which then cross in our interaction volume here. The gas is injected with a small needle, essentially a small needle valve that puts a jet of CS2 into that interaction region. And then some 3 meters downstream, we have our phosphor screen detector and camera on the back to allow us to pick up the scattered electrons that come through the system. And that gives us images that look something like this. So hopefully you can pick this out. So we've got a hole in the center of the detector to let the undiffracted electrons pass through. We center the electrons slightly off the actual center of that hole so we can try and capture as much of the scattering, small angle scattering as possible. And then you can see kind of there's concentric rings or ring structures that relate to the separations within the molecule. So the temporal resolution on these experiments is probably what currently limits the majority of what we can see. So we've got a resolution of around 150 femtoseconds, which predominantly comes from the bunch length of our electrons. Okay. And we can take all these diffraction images, we can collect our pump probe data set, and we can start to look at changes in those diffraction pattern. And the way we do this is we try and look at what we call a delta I over I signal. So we take the intensity measured at a particular pump probe delay, and we subtract from that the intensity of our signal before time 0. So that's the scattering intensity of our ground state equilibrium geometry molecule, if you like. That's our static structure that we're using as our reference. Because in these diffraction experiments, there's a large cutoff or a sharp decrease, should I say, in the scattering intensity as a function of that angle out from the center of the scattering pattern. We then divide through by this scattering pattern to try and normalize the change in signal, and then multiply by 100 to turn it into a percentage. And so that's what we have here. So we have essentially a plot of the momentum transfer or the scattering angle. So this is radially integrated around all of those images as a function of our pump probe delay. So as you would expect, before time 0, we have this flat background, essentially 0 until we have our pump coming in. And then we start to see these time dependent features appearing in our scattering signal. So the strongest features are centered around this sort of 4 inverse angstroms momentum transfer. We see a strong depletion value slightly above this, and a strong enhancement of values slightly below this. Those sort of oscillations in increased and depleted intensities then carry on. You can kind of see weaker oscillations at higher momentum transfer. But as our scattering signal is getting smaller, these become harder and harder to resolve. So we get a maximum sort of scattering angle that we can reliably measure of probably around 8 inverse angstroms if we're going to be strict about it. The total measurement goes out to about 12 inverse angstroms. And on the right-hand side, you can see lineouts for various regions of this time-dependent plot. So the first one at time 0, or negative time, sorry, shows the sort of flat line. That kind of gives you an idea of the noise within the measurements, how much fluctuations we get there, and you can see that seems pretty good. And then as we move to early times after the pump, the solid black line is our measured diffraction signal. And there is a hazy area around those, which is the errors from essentially a bootstrapping analysis of the experimental data. There aren't many strong changes in the diffraction pattern as a function of time. I think you'd probably agree. But a few that are worth highlighting are in this strong feature initially here, we do have a shift towards lower momentum transfer as a function of delay, and a broadening of this distribution. Right? So you can kind of see this shift a bit more clearly. This is marked by this line here, which is a fit to the center of that distribution as a function of delay. So we're seeing subtle changes in these diffraction patterns as a function of that pump probe delay, if you like. But I can't think in reciprocal space, unfortunately. So it's difficult to explain this in terms of the geometry changes that are occurring. So what we can try and do is we can at least get a first approximation of what the molecule is doing by performing a sign transform. So these periodic oscillations are related to essentially the spacings between our pairs of atoms within our molecule. So you've got a sign R, where R is the distance between our features, that produces this total scattering pattern that we're seeing here, or this different scattering pattern that we're seeing here. And so we can perform a sign transform and get at least an approximate measure of the pair distribution function, or the change in pair distribution function that we're seeing for the molecule. So this is the sign transform. So the sign transform is performed on the data on the previous slide. And there's a few things that you always have to be careful with in these sign transforms. Ideally, we want this to be over all scattering angles there can be, but we have a finite data set. So we essentially have to truncate our data set and try and extrapolate down to some zero line so we don't get edge effects in the sign transform. And what this does is it really limits the resolution that you can see in these systems. So when we do the sign transform, we can see these very broad regions of enhancement and depletion as a function of pump probe delay. The depletions that we see, so we've labeled them A and C here, are essentially at the ground state equilibrium distances between our carbon and sulfur and our sulfur-sulfur distances. So that shows us that we're changing the geometry of our molecule is changing from what it was in that equilibrium ground state. Trying to then understand the enhancements is hampered by not only the resolution from the sign transform, but also from the time profile of the electron pulses that we have at the moment. So ideally, we'd like to see that sort of bending and stretching motion that the Suzuki experiments show in the photoelectron spectroscopy experiments. But there they had a resolution of something like an order of magnitude shorter than we have currently from the electron diffraction. So we can't see the oscillations in that bending and stretching motion. What we see is essentially a broadening of that distribution associated with the average change. Looking at this a bit more closely, you can also see how at early times there seems to be a higher intensity in these intermediate regions where we've got the sort of broader distribution, and that decays over time to a lower level. And we can take some lineouts associated with these. So if we look at those individual regions, so A and C are again those depletion regions associated with taking population out of those ground state equilibrium geometries. And then in those intermediate regions, so B and D, we see a rise as we broaden this distribution, we go to more bent angles, stretched bonds, and then a depletion on the time scale of around 2 picoseconds time constant if you assume an exponential decay. And that, we believe, is due to essentially the dissociation of the molecule. So the molecule, the CS, one of the CS bonds breaking as a function of pump probe delay. Okay. So directly from experiment, we can get a rough handle on what the molecule's doing, but we have to undergo a few sort of transforms from the data, which really hinders the resolution that you can get and isn't really a direct reproduction of how good the experimental data is. So a far better way to actually try and extract what's going on in these systems is to use theory and to try and use theory to give you calculated diffraction patterns that you can then fit to your experiment directly. So this is really preliminary theory analysis for now. So this is work done by Adam Kirander and his group, who I think are talking next week, which would be a great thing to see. And so this is based on some of their classical trajectories on the CS2 system. So done at the CAS 10.8 level. This is seen to be essentially a good compromise and gives relatively accurate barrier heights compared to the sort of benchmark MRCI theory level that they've looked at as the highest level of theory. Unfortunately, it's too computationally expensive to run trajectories on such potentials. And so what we've done there is we've used the trajectories calculated, and there's 200 of them or so, and we've weighted those or fit the weight of those trajectories to try and match the experimental signals. And that's kind of what you see in these red dashed lines currently. Again, this is a preliminary fit based on what we've done so far. There are a few details to iron out in terms of misunderstandings between what the experiment and what the theory are actually simulating that we need to work through. But the information we get seems consistent with what we know about the system as a whole. So we're fairly confident that the overall picture will remain the same. So if we take the details from these trajectories, we can get essentially branching ratios for the dissociation dynamics, which comes out at around 2.5. So that's in good agreement with all the previous measurements that are going on. And we also see that the dynamics seem to suggest we've got really rapid dissociation in the singlet states, followed by a delayed triplet state dissociation over a much longer timescale. So we're starting to get some information there about the structural dynamics, but we're really hampered by, well, I guess two things. One is the temporal resolution of the experiment. If we really want to look at vibrational dynamics and things as molecules change, then we need to get on the timescales of vibrational motion, which is typically on the few tens or below femtosecond sort of timescale. And we also need to work out ways that we can extend the region over which we can collect these scattering signals. So if we want to do a direct transform from the measured scattering pattern into those pair distribution functions, then we probably need to expand this by about a factor of 2 or so. Okay, so that's our sort of first foray into the sort of measurement of structural dynamics. In the second sort of part of the talk, I wanted to cover the electronic spectroscopy side. So I want to talk about how we can use time-resolved spectroscopy, time-resolved photoelectron spectroscopy, sorry, as a global probe. So in principle, it's always been a global probe. You can ionize every configuration, every geometry of a molecule. And what's really been holding us back is the energy of the available sources that we can use to ionize molecules. So in this, another one of Albert Stolow's classic experiments where they looked at the dissociation of this NO dimer, upon excitation, they see this very broad and featureless photoelectron spectrum, which corresponds to this sort of van der Waals bound complex. As a function of time, that photoelectron spectrum changes and eventually leads to this single spike, this very sharp feature at long time delays. And that's related to this NO fragment in its A state. And the A state is very similar to the Rydberg state, so it's got a very similar potential to the ionic state. And so you get this very sharp delta V is 0 transition in your photoelectron spectrum. And so the opportunity is there to measure all of the geometries, but this is somewhat of an unusual case. So NO is the lowest ionization potential molecule, diatomic anyway, and this A state is quite high in energy already. So you can ionize this just with a simple UV pulse. I think this was around 280 nanometers or something like that. But even in this case, you're not measuring all of the fragments you produce. So there may be some secrets hidden in the other co-fragments that tells you more about the dynamics. So what do you really need if you want to generate a global and general probe for all photochemical processes? So to my mind, you're going to need high energy. So high enough energy that you can be above the ionization potential of all potential atoms or molecular fragments that you might be interested in measuring. So that means you probably want to be somewhere around 16 to 24 eV. So 16 eV takes you above the ionization potential of pretty much everything, and 24 eV keeps you below the ionization potential of helium, which typically we're going to try and use as a seed gas to try and get our samples into the gas phase so that we can actually measure them. So that kind of gives us a sweet spot in energy that we want to be at. We're going to need ultra short pulse duration, and we're more than likely going to need long-term stability, or we're going to have to measure these things really accurately. We're going to be looking at small signals on big backgrounds. So if we have temporal and spectral stability, that makes extracting all of that information much easier to do than it would be if you've got something that's oscillating all over the place. And it probably won't surprise anyone here that the way we do this is through high harmonic generation. So high harmonic generation, for those who aren't aware, is just a strong field process by which we can generate very high order harmonics of the fundamental driving frequency of laser. So if you have a strong laser field, when you're at the peak of that laser field, you can tip the Coulomb potential of the atom that you're interacting with, such that your electron can tunnel out of this small barrier and escape. As this electric field oscillates, it can change sort of direction. So it can first have this free electron accelerating away and then back towards the ion that it's left. And upon recombination, it can release all the kinetic energy it's gained in this sort of acceleration process back as a high energy photon. So if you've got a relatively long laser pulse, this oscillation goes backwards and forwards, and you get multiple cycles of this ionization, acceleration, recombination process, which generates a frequency comb of different harmonics. If we try and use all of those harmonics as the frequency comb, because we're going to be worrying about relatively complex photoelectron spectra, we're going to start getting lots of overlapping photoelectron bands. So we're going to want to try and isolate one of those harmonics to give us the best spectral resolution we can get in these experiments while maintaining some good temporal resolution. So these experiments were done at the Artemis beamline. So the Artemis team have been strong and constant collaborators of mine for the past decade or so, and it's always great to work with them. This is a quick whistle-stop tour of the beamline that we used at the time. So we have a Red Dragon base laser producing approximately 12 millijoules on a good day. This is separated between two independently controllable compressors. So one of those compressors will be used to generate our pump. So we've got some standard fourth harmonic generation nonlinear optics and a delay line to control the relative delays. And the other arm goes into the high harmonic generation chambers. So we have, first of all, a second harmonic generation crystal to generate the second harmonic at 400 nanometers, which we then focus into the gas jet for generating the harmonics. So the reason we use the second harmonic is we find it generally increases the efficiency of generation for these low energy harmonics. And it also gives you better spacing between your harmonics, so you don't have to worry about any sidebands or anything like that. This then goes into the clever part of Artemis, which is this time-preserving monochromator, where we have toroidal mirrors focusing onto a grating where the lines are perpendicular to the way you might usually expect them. This is then focused into our interaction chamber where we have a time-of-flight electron spectrometer. Out of this system, we can typically get harmonics in the range, I would say 10 is probably a bit low, but somewhere in the range of 16 to 100 EV. And typically we're looking at harmonics on the order of sub 30 femtoseconds in duration once monochromated. And that's from approximately 30 femtosecond driving field. And so then we're going to go and do the photoelectron spectroscopy experiments on CS2. And so this is a plot of our photoelectron intensity as a function of binding energy. So binding energy is the photon energy of our ionizing pulse minus the electron kinetic energy, so how much excess energy our electron takes away. And then this gives us an idea of which orbitals we're going to be ionizing within our system. So this feature here relates to ionization of the ground neutral state into the ground cation state, for example. Believe it or not, but there are actually two spectra superimposed on here. One that is our pre-time zero background, so just the measurement of our ground state molecule, and one that's occurring at asymptotically long times, about 10 picoseconds or so after excitation. And if we zoom in on this sort of region between the two main peaks, you can start to see the difference in features that we're seeing in our photoelectron spectrum. So you can see these extra bands that are starting to occur at the longer delay times. And this again highlights that need for a really stable temporally and spectrally system if you're going to try and pick out features on these relatively large backgrounds that are so small. If we do that background subtraction, then we can start to assign these features. And here we have a plot of our ground state spectrum in black. And then we have our spectrum at what we might call early times, so within the first 500 femtoseconds or so after excitation, where we can see the electronically excited states. And then at longer times, so after about 4 picoseconds, we can see the spectrum associated with the various fragment products that are being formed within our system. These assignments over here give you an idea of how we might be able to look at the time profiles of various things, so we can see where you would expect bands related to the different dissociation products. But you can also see how they're all very close together in energy. So we're going to get lots of overlapping bands that we have to try and deconvolve somehow in our spectrum. The excited state signals are much smaller than these product state signals. They're much shorter lived. They have much lower ionization cross sections. And so these are really sensitive and really difficult to measure generally with the XUV pulse. But if we take the time profile, like we did for the electron diffraction, so this time we've got our pump probe delay along the y-axis here, and our binding energy axis along the x-axis here. At early times, we have this relatively flat baseline. And then as we move later, initially, we've got signals at these low binding energies associated with our singlet excited state population. Slightly delayed to that, we have slightly higher binding energy features associated with the triplet electronic states. And then at longer delays still, we start to see the fragmentation products starting to appear in the spectrum. And we can zoom in on particular points, and you can start to see how we see the transitions between the various fragments as this molecule starts to fall apart, and we move towards the ionization limits associated with the fragments from the molecular ionization potentials we had before. So these are really beautiful and detailed maps of the electronic dynamics that are going on within these systems. This is essentially the same data again, but with a slightly different background subtraction. So what we've done in this case is, instead of taking the full background observed at pre-time 0, we scale that background to just subtract the unexcited molecular components. So now we have the bands associated with our molecules. So this is about 2% of our molecules that we excite. And then as we go to time 0, that population is depleted, and we see the enhancement in these excited states, and then the formation of these products. And that allows us to get a better handle on how features that are overlapping with those ground state initial peaks are changing as a function of time. So then once we've done that analysis, we can start to look at the time profiles, and we can look at the changes. The red lines are fits to a kinetic model, which I'll touch on in a few moments. But the other thing that we can do is, if we look at those late times, we can start to deconvolve the spectrum into peaks associated with the various fragments. So the widths and the positions of these are from various other measurements of frequency resolved measurements, trying to look at velocity distributions of fragments and vibrational distributions of fragments. And so we have a good idea of where we should expect these things. And from that deconvolved photoelectron spectrum, we can get a branching ratio that again broadly agrees with all the other measurements. So now we're around 2.3 to 1. So we're really homing in on that 2.5-ish sort of ballpark for the branching ratio here. So what that branching ratio measurement allows us to do is it allows us to look at this kinetic model in slightly more detail. So if we think we've got initial excitation into these singlet states, and then we have a branching between the singlet dissociation channel and the intersystem crossing into the triplet channel, instead of looking at what is an effective lifetime of these states, we can now look at the separated time constants associated with those different fragments. And so that's what we do. So those fits on the previous slide are essentially fits to a kinetic model of this form, where we have initial population into our CS2 singlet states. Unfortunately, we don't have the time resolution to separate out the individual components in either the singlet or the triplet manifolds. Whether we could do that energetically anyway is another question. From the lifetimes, we can actually pull out the actual time constants associated with both the dissociation and the intersystem crossing process, which gives us our ratio of branching. And then from that, we then got our dissociation into the final triplet states. So by increasing the energy of our photoelectron probe, we've really generated a very sensitive probe of chemical dynamics using photoelectron spectroscopy, which has been around for generations and has taught us most of what we know about bonding structure in molecules. It allows us to monitor all of the states involved and all of the products, but it does highlight many of the challenges that we're going to encounter if we move beyond these sort of model systems. But I think it does highlight that even in these model systems, we do need to measure all of the components within there if we're going to get a real handle on what's going on inside. So what are the challenges for these global probes? I think two things come out from these experiments, or three things maybe. One of the main things is that the dynamic signals are not always easily assignable. So it's difficult to go from an experimental measurement to a direct assignment unless you have a lot of background information on the systems themselves and unless they're very simple. So that means we really require theory at an accuracy that can give us, well, chemical accuracy, so we can change the pump wavelengths and see the effects of different vibrational excitation. I think it's a real challenge for quantum molecular dynamics simulations now. And we also need those calculations to explicitly include the observable that people are measuring. So just seeing timescales that match those dynamics calculations, I think now is no longer being good enough, if you like. We really require that explicit inclusion of the observable to get us a direct comparison between experiment and theory. Like we sort of described in the scattering experiments, you really want to go from the observable and the theory, and from that generate your understanding of what the molecule's doing. So this is maybe just a feature of these. The signals are small. Typically, they're on the order of a few percent. So in the photoelectron spectroscopy experiments, we had about a 2% excitation fraction. That gave us approximately 1% or 2% in the product channels coming out, because it's spread over a much more diffuse band, generally because of the vibrational excitation you get. In the diffraction experiments, it was on the order of 1% again. And again, this really brings out the ideas of requiring either good diagnostics of your pump and probe, so that you can maybe normalize or calculate the effective signals that you should be getting, or you need really good stability. And high harmonic generation is an example where the stability can be exceptionally really good. And the other challenging thing that maybe we can do something about experimentally is that the spectra are convoluted or congested. So if we look at the spectrum associated with the products in this CS2 molecule, so we've only really got 3 potential fragments, which, you know, for a molecule with 3 atoms, that's quite a lot, but in terms of chemistry as a whole, we're going to get much more diffuse spectra from larger molecules, much more possibilities for different diffraction patterns, different isomers that we're going to need to try and deconvolve somehow. And this is maybe where photoelectron spectroscopy has some advantages. So if we go back to the discussion on Albert's experiments in CS2, a lot of the extra information they derived from the photoelectron angular distributions. And so moving towards measuring photoelectron angular distributions in many of these systems is something that requires a lot of development of the sources. If you think of the detail contained within these experiments and then look at actually what range of geometries and states this was actually measuring, it's quite remarkable the amount that they managed to extract. So if this is our map of the full dynamics of the system, the probe in this experiment is really only measuring this tiny little component at these lowest binding energies measured by our experiment. Yet they could extract really intricate and intimate details about the electronic structure changes. So extending these measurements to include photoelectron angular distributions would be a major step change in what we can understand in the dynamics of these systems, and maybe allows us to separate out the various components within the wave packet. Unfortunately, photon fluxes aren't quite there yet. High rep rate laser systems are now moving forward, and hopefully in a few years' time we'll be in a position to actually measure full photoelectron angular distributions, at least for these higher, lower binding energy features down here anyway. On top of the ground state background, it's always going to be a challenge. For the products though, the other thing we can do is start to look at ways we can measure both ions and electrons in coincidence. So if we can increase the rep rate of these laser systems, maybe to 50 or 100 kilohertz or so, we can then start to count the electrons and the ions. We can collect both the energy of the electrons and the ions that they come from, and then start to correlate those either through coincidence or covariance methods to try and separate out that very complex and overlapping spectrum. That way we separate them out experimentally. We don't have to rely on fits to the spectra. We can do this right up front. So I think there's lots of prospects and opportunities, and there's lots of light sources that are coming online that would give us the opportunities to do these. And I think that I'm just about on time. So I think that brings me to the end of what I wanted to say today. There are a few acknowledgements of the people that really did the work. For the electron diffraction experiments, as I mentioned up front, Rory Forbes was really the person who drove that. So he was the PI on the beam time, but the analysis was all done by Veronica in Southampton of the experimental data. The photoelectron spectroscopy work was done by Adam and Emily, and that was done at Artemis, and these guys deserve a lot of credit for getting the experiments working and for all the beamlines and work that they do as well. Adam, as I mentioned, Adam Kirander's group, they've been constant theory collaborators of ours, and he's worked on the CS2 problem for a number of years with us now, with both Darren and Carl as students doing the electronic structure and trajectory calculations and diffraction calculations for us as well. Finally, I should thank the Royal Society, EPSRC, Leverhulme for research funding, University of Southampton, STFC and Central Laser Facilities and LCLS, finally for access to the facilities. And with that, I think I'll hand back.
Okay, thank you, Russell, for the really nice talk. Now, please put your questions in the Q&A tab or raise your hand. And before we start with the questions, I would like to make an announcement, namely that we have a special issue that's open. It's called Quantum Aspects of Atto Science. I know a lot of you have already contributed. It's associated with the conference last year, Quantum Battles in Atto Science, but we have talked to the editors because there was a lot of disruption due to the pandemic, and we are still accepting contributions, and we have invited all the speakers of this series also to contribute. So if you would like to make a contribution, feel free to drop me an email, and give me more or less a date in which you're going to submit. If it's not too far away, the editors have assured me that this is going to be fine. And we are still accepting our contributions, and a lot of people are in contact with us as well. So are there questions, comments? You mentioned, okay, while we're waiting, you mentioned that there was a prospect of using a lot of the studies and techniques that you were looking at, or people are looking at, in quantum electrodynamics. Can you explain that or elaborate? It's a very vague question, but I think we have audience, so people are curious.
I hopefully didn't mention quantum electrodynamics.
I think it did.
I hope not.
Because I thought it looked weird, but okay, never mind.
So maybe I meant electron dynamics. So electron dynamics in molecules are essentially quantum. So it may well be I meant it in that sense rather than the true meaning of quantum electrodynamics.
Yeah. Yes, because electron dynamics is being a goal that everybody is aiming at, right? And we can see that you have been studying quite a lot in the chemistry direction. So a question I think that we all have is, you say you are struggling still with many things. So in your opinion, what is the next challenge? What is the biggest challenge that you're facing?
So it's, well, I can split that out in two ways. Generally in the field, I think the biggest hurdle is now the accurate simulations and calculations of observables. Mm-hmm. I think for the first time in, I don't know, first time in a long time, experiment is now leading theory in terms of what we can see. So we really need theory to be able to accurately calculate the quantum dynamics and the observables across a wide range of techniques to give us that insight. In terms of the experimental opportunities, some of it is kind of in development and on its way. So producing shorter UV pulses. So generating deep UV pulses on the order of a few tens of femtoseconds is now starting to be possible via these hollow cooled fiber approaches. And that then seriously removes many of the limits on time resolution that we currently have. Mm-hmm. So yeah, I think those are two of the things. And then the other thing we always battle, particularly in photoelectron spectroscopy, is photon flux. But if you consider the sort of Red Dragon system, that was kind of a 12 watt, 1 kilohertz laser system. If you look at some of the fiber laser systems, hundreds of watts is not an issue at rep rates that are significantly higher. And those start to become game changing in terms of the signals that you can start to extract and the molecules that you could start to look at.
Mm-hmm. But also you mentioned these short pulses. I mean, if you have a very short pulse, another challenge that you're going to have is that you are going to have a broad bandwidth, right? And then you mentioned at the very beginning that you struggle if you have a spaghetti of states that you're trying to understand that get coherently excited. So how do you deal with this?
It's inevitably a system by system compromise. I mean, it would be great if you could just dial up the pulse duration that mapped the dynamics that you wanted to. So take, for example, if your dynamics are, I don't know, IVR driven, then probably a picosecond pulse would be ideal, because then you can really control the vibrational makeup of your vibrational wave packet. You can get high resolution in your photoelectron spectrum, and you can map out the dynamics on the appropriate timescale. If you're looking at some of the other dynamics, you're going to have to go much quicker and try and deal with the spaghetti of electronic states. And it's kind of, at the moment, we kind of compromise. We deal with the instruments we've got and we see what we get, but they're rarely, I would say, ideal, because we can't just tune to where we want to be.
Mm-hmm. Mm-hmm. Okay, we have a question from Raluca Serraza. A technical question: the photon flux of the high harmonic generation probe at 21 electron volts and the parameters of generation. Could you elaborate on that?
So we generated about, so on target, we get about 10 to the 10 photons per second. And so parameters of generation, so we have about 500 microjoules of 400 nanometers. So that's on the order of around 40, 45 femtoseconds, focused into a argon gas cell of about 2 millimeters in length, approximately. I think those are the main parameters. If there are other ones, let me know.
Yes, would you like to ask further? She's saying thanks, but if you would like to ask further, let us know. We put you through. Is there anybody who would like to raise their hand, ask a question? Do feel free to do so. You will have the opportunity also to ask. Thank you. And the flux, there's a mention here from the same person that the photo flux is very high or seems very high.
We work hard.
They're wondering.
I mean, the throughput on, so the throughput on the monochromator is around 30% of what we generate. So, I mean, we typically generate more than that at source, but then we've got losses on the throughput. We certainly generate about, by going to generation with a 400, sorry, we generate about 20 times more than we do just using the raw output of the 800 nanometer light. So that gives us an order of magnitude or more higher photon flux. So that's the thing that made the biggest difference for us.
Okay, would you like to pursue further, ask a question? Do feel free to ask. No, it doesn't seem like it.
I mean, Raluca, if you want to drop me an email, we can have a chat offline on the technical details if you want to know a bit more. Okay,
we're going also out of YouTube pretty soon, because now it's being streamed. So my crazy question about quantum electrodynamics, because I misunderstood what you said, went on YouTube, but I'm too old to care about this stuff. Oh, yes. So take care, everybody who is watching on YouTube. Thank you for your support. Those who would like to ask questions more privately, just hang in there. And all of you, thank you for supporting our initiative in these really difficult times. So YouTube people, bye. Have a great weekend. See you next week, hopefully.